All right, so can you hear me all? Okay, great. So I'm Timur from Nevada. So first of all, I'd like to thank Simon and Mikal for inviting me to this wonderful workshop, which I have been enjoying since 2023. So, well, not continuously, but when I came here. So, but this is work done in collaboration with my wonderful group, and this was most of the work was done by Hubert and my graduate student MD, but I also tell you a little bit about the work that was done by Nathan Prince. So, okay, let's get started. Um, we heard much about about shielding, so I'm not going to talk about shielding. Okay, so just a full disclosure for today, right? But I think shielding is a wonderful tool which finally has been able, of course, to shield us from inelastic collisions, losses, but what I'm going to argue in this talk generally is that yeah, what are some of these wonderful unexplored opportunities that basically await us in this short range region, right? So what can happen that is not just lossy and bad, but good, genuinely good. Okay. So I'll try to convince you, but of course it's largely an open problem because, like John mentioned during the panel meeting, the sticky collision mystery is still a mystery, so hasn't been solved. Then there's also a very interesting set of experiments, actually recently done on magnetic Feshbach resonances in atom-molecule collisions, and those resonances are not completely understood. The precision mapping of microscopic interactions in the reaction complex is something that most chemists would find fascinating. And for example, the group of Christiane Koch and Markus Mülly in Europe, they have been actually really blazing the trail in this direction, using high quality potentials and then morphing them based on highly precise collision measurements, basically into something that is wonderfully precise. So something like that would be a dream to do, of course, for more complex chemical system collision complexes. Another recent direction that was started largely by Canquen's Nice group is what about if we think like producing entangled pairs of molecules starting from chemical reactions? Let's say we can entangle KRB molecules, but how about K2 plus RB2 products, right? Because it's a chemical event, they are going to be entangled, and what kind of entanglement that is not fully clear yet. With something that we have been working on. And this is a wonderful thing, for example, to think about using all these entangled pairs of molecules that are fully controlled for things like quantum teleportation and other feats of quantum information science that can, imagine like teleporting a product somewhere. That would be nice, right? So, so, well, of course, this is more for science fiction, but there actually been a PRL on that. So I can give you a reference, although the proposal seems to be far-fetched. So another interesting thing would be to do full quantum scattering state tomography, which is a full characterization of the S matrix, including not only probabilities and phases. And once this is done for a reaction for KLB, then scattering theorists can pretty much retire because there's nothing everything could be measured, and S matrix is the ultimate, arbiter of truth. So there's nothing else you can possibly do. And then, but I think we still have time. I still have maybe 20 years before I retire. So I'll try to maybe bring this to fruition. So there are interesting things, but of course, this is one example of this is recent paper that we wrote with collaboration with Kanquensny's group and John and Mikal and his group. This is one example of a process that is challenging to understand without invoking the short-range physics. And that is, for example, the energy transfer that is inherently mediated by short-range interactions. For example, rubidium in the first excited hyperfine state colliding with KRB in the ground state, going over to the rubidium in the ground state, and KRB was formed in a different set of rotational states. So of course, this could only happen if spins are actively involved at cold collisions, because usually the potential on the surface is diagonal in all spin quantum numbers. So this must be something that depends very strongly on spins, and that was occurring at very fast, actually, near closing universal rate. So And so for that, we need something like a rigorous quantum scattering calculation. I'm not going to shock you with details, but there's basically 6 angular momenta. So there's like maybe 51. You can think of coupling them into 51J symbol, which is something that I think the largest the largest NJ3 NJ symbol that has ever been published. Although there are different opinions about that. So, so basically you have to do a lot of angular momentum algebra, but you also have to be careful about basis sets, because some of the basis sets will give you converged results, which means they efficiently represent the basis function. Some of the ones, some of the other basis sets will not give you converged results, but we have included all of these interactions. And in fact, even after we included these interactions, and Mikhail did a wonderful job at calculating the potential energy surface, and there's a conical intersection, there's spin, so all of these are spin dependent interactions. So these A's, for example, constants are, they are coefficients in front of these terms, and these look like potential energy surface term, but this is really Fermi contact hyperfine potential energy surface. So this Fermi contact interaction actually depends on the intermolecular distance or atomolecular distance and angle, Jacobi angle, as shown in this plot. So these are, by the way, those 6 angular momenta here. There's also orbital angular momentum and rotational angular momentum of the molecule, which are not shown. But basically, there's a lot of angular momentum, and they couple in complicated ways. And you include, when you include them all, you still cannot, or I cannot reproduce the experiment, right? And that was a little bit, an interesting experience, so to speak. So after maybe a year and a half doing calculations, all we could, basically that was not. You see, this is what theory predicted for a bunch of different interaction potentials, like a histogramming, results showing that n equal to 2 is the smallest channel, but n equal to 0 is dominantly populated, and then that was just exact opposite to experiment. So it was just exactly diametrically opposite to what was observed in experiment. So from this, we could actually make it, because we included everything pretty much in this calculation, other than this conical intersection that Mikhail found. So that must be due to conical intersection then. But how to include this conical intersection, no one knows, because we already going up against the absolute limit on the number of channels and states that can be included. So my computers have been repeatedly, suffering, even though I bought some of the best computers, spent a lot of money when I was just hired like 10 years ago. And I spent maybe, I remember like maybe 30% of my startup on just huge computers with a lot of memory, like I have one with 1 terabyte of RAM. So I can store, I can store 20,000 channels and even 50,000 channels in memory, in RAM. But the problem is that just too slow. I have to wait for such a long time that calculation becomes like a lightning strike. So we have like lightning storms in Nevada in May, like they go like every week. And like, it's a bad time for me because like I have to like basically, restart all the calculations again. So they cannot take more than 1 year. That's kind of my personal cutoff. But actually, this is just a metaphor maybe. If so, like to just bring home the need for larger couple channel calculations. If we had this access to, let's say, we could solve, I don't know, 100,000 channels, wouldn't that be nice? We could figure out the conical intersection. We could figure out the vibrational degrees of freedom. Maybe we could figure out the whole quantum dynamics of at least atom molecule. I'm not even trying to say something about the sticky problem of potassium, rubidium plus potassium. So short range is hard, right? As we have heard, and it requires large system coupled equations to be efficiently, solvable on computers. So these are some of the challenges. So this is like more like quantitative. I estimate, for example, one can make some estimates. For example, sodium, potassium, right? It's a famous system which has sticky collisions, despite the fact that apparently there's no open channels so there's no chemical reaction, and the light seems to play no role in this. So light was turned on and off, and then the rate for nothing changed pretty much. So, but that would require at least more than at least 100K channels. Now, current limit is about 20K channels. We're about factor of 5, but I think this is just rigid rotor. Of course, this system is very complicated. But let's say if I wanted to do adiabatic curves that John showed and Ty showed and Jeremy showed, and they were showing these curves at about several hundred Bohrs. If I want to continue them down to maybe, 10 Bohrs, I would have to include that many channels, because if we're interested to see what happens inside this, when the short range becomes important, we have to include progressively more and more. But of course, the full problem of potassium, it would be millions, unless something dramatic happens. And the problem is that the computational effort scales like n cube in the conventional method of solving coupled channel equations, because we have to deal with matrices, and I'll tell you more about this soon. But so I'm going to talk about today about more efficient quantum dynamics algorithms that we have been developing in my group. But there's also other multiple issues, of course, with short range. For example, uncertainties in potential energy surfaces and phys, the sensitivity to those things is completely unexplored because we cannot solve these huge systems of coupled equations. And what lies in that region is unknown. So I get excited by this unknown. So I basically try to, I'm challenged by this, and let's see what happens, right? Why cannot we solve? Like, we have to dig down to fundamental reason. Why cannot we solve more than 20K channels? And the fundamental reason is because if you look at this Hamiltonian, let's say I've just take atom rigid order Hamiltonian and expand the wave function and get this, familiar coupled equations from the 60s, right? So the problem is that, well, you have to deal with the matrix. So this U lambda lambda naught is the full matrix of solutions. And even if you're dealing with a single initial state, let's say lambda naught, you actually need the full matrix. So all the methods that have been developed so far, most of them, actually propagate the whole biometrics of solutions, or to be precise, its log derivative, or the Numerov. They use the Numerov method, which is the ratio of these functions at neighboring rim points, right? So like here I did some definitions. So lambda, for example, is a channel. So it's just a state in atom molecule system that is just like general state, which it has, for example, little j, rotational angular momentum, orbital angular momentum, total angular momentum, projection, all these quantum numbers that are good included in this lambda. Okay, so lambda is a collective index, composite index for these channels, and v lambda lambda prime play a big role in the subsequent discussion. Is the matrix element of the potential, the reaction potential, which you calculate. It's just integral of the, in this case, atom rigid order potential, and little r is this capital. It should be little r. It will be converted to little r soon. So it's a distance between atom molecules. So this is the only distance you do not really expand in basis sets, and then you solve the system of equation. So because it's a matrix, right, you have to deal with n-cube computational scaling, and so basically you're left with very limited choices. Either you come up with a very efficient basis set, which is something that we have been playing with, or you have to beg mathematicians or computer scientists for more efficient inversion algorithms, right? Which actually recently there have been some interesting developments, at least like they got it down from cube to 2.6, which is like, I didn't know that. And so I don't know if it has been implemented, but there have been some papers. So that looks very good for log derivative methods. So, but there's a more dramatic way. We can think of just neglecting solving for a single column of the S matrix rather than the whole matrix, because in ultra-cold experiments, and this is a crucial point, we often start in a single state of the molecule, right? So we need the whole matrix. Why? Why do you need the whole matrix? We just need a single column. And if we just need a single column, then we can just shave down this computational cost from cube to quadratic, just right very quickly. Well, it's not so. There is a reason people use the log derivative matrix, and people tried this before, and it wasn't. They encountered some hurdles. So I'm going to tell you about that. So first of all, I just want to announce the people who did most of the work, and this basis set optimization was my graduate student Nathan Prince, who is very talented, and the rest of the work and the most of the work I'll be talking about will be done by Hubert and MD, who are wonderful. Hubert is now a postdoc, I think, and MD is a graduate student. So wonderful collaborators. So the quick reminder of basis set optimization. So what you do pretty much, so you start with some log derivative matrix, and you go across a sector. You propagate it. You just basically inch forward in this atom molecule distance, and then you apply some boundary conditions. So the basis set site typically in many current codes, for example, the ABC scattering code, which is used by many chemical physicists, the basis set is independent of the atom molecule distance. But what if we thought, what if we examine the log derivative matrix and actually discard weakly coupled channel from the log derivative matrix? Would that help in the basis set? The point of this is basically to show you that it's actually a vastly unexplored field. So people are wasting computational time like all the time, because for example, like in this case, we can think of like, well, why haven't anyone tried this? And it's a good question. I don't know the answer to that, but basically, if you do that, you can actually go to you can start, depending on the basis set, you can go down in computational, in propagation basis set very quickly down to about actually 20. If you start like for the system MGNH, you dynamically or R-dependently truncate your basis set. You can do that, and by just throwing away the log derivative matrix elements that are smaller than a threshold, some threshold, you can actually get down to only open channels at about, when you reach the long range. For this system, it happens at fairly short molecule distances. You can basically, you can do way better, at least a factor of 10. But if you're propagating out to long range, you can do up to several thousand times better. So this is just one example. There are many other examples. This field, there aren't many people working in this field. So this is, this is something actually you can implement if you have a couple channel code. It's very easy to implement. You just take your log derivative matrix and, I think I went, so, and then you take it and then you truncate it, that's it. So the other thing that is actually even more dramatic is like what I just said, like you can try to solve, instead of the couple channel equation, you just solve the Lippmann-Schwinger equation, which is the integral equivalent. And turns out there was a guy who named Lowell Thomas who tried to do it in 1979 for atom molecule scattering. But then there's actually, that's his picture. So this is actually June 27th, 1979, there was a historic workshop in Argonne National Lab. And you can recognize, if you have been doing quantum scattering calculations for a while, you can recognize some of the famous faces here in the field. Like, for example, some of them unfortunately are no longer with us, like John Light and Don Sechrest and Greg Parker, I think. Parker, also Millard Alexander is here. So, and many people who shaped the field actually attended that workshop. They developed these foundational algorithms. And Lowell Thomas is here. And this is the only picture that I have that there exists of this person. So there's actually an interesting story. I have been like, he kind of, I don't know what happened to him after this workshop. After a few years, he published his last paper and then he disappeared. So if you search for him on the internet, or I've been asking people about him, no one remembers anything. So if you do know something about Lowell Thomas, please write me an email or approach me so I can thank him for his amazing contribution, which I'm going to tell you about in a second. So it was way ahead of its time. So what he did is he basically wrote down the Lippmann-Schwinger equation, which is a full equivalent of the coupled channel equations, right? So you get this unperturbed solution on, just a plane wave, roughly speaking, right? An unperturbed Born, scattering solution. And then he has a green function. Of course, this is, out of any quantum mechanics textbook, you see that, right? This is in Cohen-Tanucci, for example, but it's just multi-channel version. So you need the Green's functions in real space, and then you need potential, and then you need your solutions, right? So solutions are expressed in terms of themselves. Of course, this suggests iteration, right? So you basically plug in. So just a few words on the Green's function. The Green's function is really simple to calculate. It's just the product of two regular and irregular solutions of the Schrödinger equation, with all the channels, with all the couplings between channels neglected. So it's really, well, I'm saying it's straightforward, but Hubert may disagree with me because he spent, I think, several months, but I'll tell you why it's not entirely straightforward, because Thomas, turns out, only considered open channels in his formalism. So he didn't apparently worry about closed channels, which is kind of interesting because closed channels are very important for getting converged solutions. But at that time, it was, imagine, 1979, it was like 46 years ago. And people actually didn't realize, I thought, that, closed channels are even required to get solutions. So it was such a, it was a dawn, like, really, of the field. So anyway, so this is it, right? So all you have to do, you just take your regular solutions, and then the nice thing about this, right? So about, like, if you go back a little bit to Green's functions, is that the Green's function has two faces, right? It has R and R prime. So it's a kernel of an integral equation. So it actually, the dependence on R that goes through this irregular solutions, it actually ensures the correct boundary conditions at infinity and at 0. And this is amazing because if you, this is, gives you just the right boundary conditions, just pop out of the equation, right? So that's why it's great. So, and you can also write it in matrix form like this, right? So with this being G being diagonal matrix and V is the matrix of your interaction potential. Okay, so Born iterations, you basically plug, some plane wave, and then you start your iterations. This is some technical details. You can find them in these papers by Lowell Thomas. So, okay, so what do you get? So Hubert did it, and wow, lo and behold, you have convergence. So we pick a simple test problem of helium collisions at 5 Kelvin. It's not a trivial problem because inelastic scattering is pretty strong. It's not like super strong, but it's quite substantial. You see that after about 17 iterations, with just only open channels, you get converged solutions that are in exact agreement with, with full coupled channel calculations. So it works, right? So, but, okay, so before I, shatter this picture, but I'm gonna like tell you first about how it works, right? For as a function of collision energy, actually, the convergence is pretty good. Although if you look at the cross section of function collision energy, because you don't include closed channels, of course, there are no resonances, right? So it's not a very good, actually. So you see this converged close coupling is this gray curve, and the Born iteration with Thomas is two channel open channel solution is in perfect agreement with coupled channel, which only has two open channels. And the number of iterations is actually 18, but then it goes up as the cross section goes up, which makes sense because the larger the cross section is, the harder it is to converge, right? And this is Born series, so basically, if the coupling is very weak, it's just enough to do one iteration pretty much. So it's just lowest order solution. Okay, so what happens if you include closed channels? That's when, the interesting things begin to happen, right? Because closed channels are not nice, right? Closed channels are, they have this, modified spherical Bessel functions on the first and third kind. They go to 0, but they blow up also if you're not careful. So you have to be careful with these coefficients, right? And you have to make sure that, for example, the A coefficient is 0, and you have regular, and this guy is irregular. So these exponential properties, they actually cause difficulties with convergence. And see what happens if you try doing iterations with closed channels. Starts to diverge actually exponentially. Instead of converging, you see this nice e to the 1, for some reason, I don't know why, but it's very well described by e to the 1.4x. So like MD fitted it, and it's perfect. And I'm not quite sure why it is so exponential. But of course, it's known, okay? So we are not like too surprised about it, because in nuclear physics, people actually did that before in the early 80s. And they saw this, so they tried to apply things like Padé approximates. But by the way, I should also note that if we scale the potential down by a factor of 10, we see that the convergence improves, which is not like, it's not convergence still, but it's not exponential either. So for weaker potential, but the point of this plot is to show that the closed channels are very detrimental to convergence. So we have to deal with them, right? Or the method is not useful. So by the way, Padé approximates actually work for, so they turn this oscillating mess into a converged result. So highly recommended if you have, not a very strong potential. But the potential, if the potential is realistic, unscaled helium cell potentials, Padé approximates still fail to actually converge. So they cannot give you the convergence even if you crank it up by, the order of Padé approximate. Padé approximate is just a rational function, is a ratio of two polynomials, which you adjust the coefficients by fitting to your orders of perturbation series. So, and it works better because it properly describes the poles in your solution. Now, this is the big gun. So we went to Fredholm theory as the ultimate solution. Of course, in mathematical physics, Fredholm theory is nice because it guarantees you the converged solution of the second kind of the Fredholm integral equation of the second kind, which is exactly what our equation is. So how do we guarantee the convergence? And actually, the method is, well, you actually turn this integral equation into a system of linear equations by discretizing the kernel. You discretize kernel on a finite grid of points. Well, and then you write it as a system of linear equations, right? And then you invert it, pretty much, right? That's it. Is it the strength is this method is not perturbative. So it's kind of perturbative, but in addition to it, you're also doing inversion, inverting a matrix. So, okay, so then you have this huge determinant that you have to calculate. It's called Fredholm determinant. And Fredholm proved in 1903 that this determinant is all you need to figure out all the scattering properties, which is nice, which is something that actually people in the 70s worked on. Bill Reinhardt and Eric Heller had some papers on it. So it's kind of known. But what is interesting that we don't have to calculate the Fredholm determinants explicitly, right? So we actually write an expansion. So this expansion is similar to the Born expansion. And if your kernel is in the trace class, fortunately, thankfully, mathematicians guarantee us, trace class means that the trace of KK dagger is less than infinity, it converges. So this thing actually converges absolutely both the numerator and denominator. So there's a theorem that you can actually write. So it's actually amazing. Well, there is, of course, the price to pay for that. You have to calculate the kernel, the trace of the nth power of kernel. And this is not for the faint of heart, right? Because look at this. This is like a path integral, pretty much, in statistical mechanics. So actually, it has very similar property to the path integral. If you look at the partition function, for example, look, it's exactly the same. of course, you know, we like, okay, so we could try path integration, but Hubert and we decided to just calculate the eigenvalues on a computer because like it seems to be, you know, easier to try as a first step, right? And so of course it kind of ruins everything because, right, you still n-cube the diagonalization and everything. So, but we wanted to see if we can get converged results and then maybe, you know, see if we can simplify the calculation of this Fredholm trace. And actually, indeed, so some of the latest results Hubert just sent me, I think yesterday or the day before. So convergence is actually here. So we can actually, by doing Fredholm iterations, instead of, you see, the Born series just diverges badly, but Fredholm converges. So some conclusions, we're very optimistic that we can actually solve the this kind of problems with better you know, computational efficiency. And as Thomas was able to solve 5 times more channels back in 1982 than his contemporaries, we're also hoping to solve 5 times more channels than our contemporaries, which is 100K, which would bring us to in some interesting systems on the verge of having converged results for these kind of systems, and maybe even molecule in the rigid rotor approximation. So that's it. Thank you for your attention.
Hey, Timo, what about chemical reactions?
In
will it work or will it?
In the form that was suggested by Lowell Thomas, probably not, because hyperspherical coordinates would be required. Yes, but I think one could develop it into something that would work also for chemical reaction. Yeah.
Okay, thank you.
So, as you know, we played with Lowell Thomas a little bit when George McBain was visiting my group about 10 years ago now. And my memory is that we got it to work in fairly simple cases like this, but that we couldn't get it to work at all well for the purpose of characterizing Feshbach resonances. And so basically when we got close to a resonance, it was breaking down. And since characterizing resonances is the most important thing in ultracold, we felt that wasn't good enough. How does yours work for mapping out the profile of a resonance?
Yes, it's a very good question. This is, I think, on our list of things to do. I think the major reason why it didn't work in the case of George was he didn't include closed channels. And because when you don't include closed channels, as we know here, right? I mean, for example, looking at this profile, right? You do not have resonances if you, so this is like a resonance. You think of this is due to a closed channel or some shape resonance. I don't know, but look at this profile with open channels. All you get is very smooth, but we have been able to include those closed channels. So that's why we call it modified Thomas algorithm or improved Thomas algorithm, because it's really essential. I agree with that, but it's hard, as we have shown you. Something like Fredholm would be required to really force the convergence. Yeah. No, but now it can be done. So we just haven't scanned Kilge energy as much, but we are more focused on making Fredholm work now because it's very important. Yeah, convergence.
So in setting up the Lippmann-Schwinger equations, you use this green function. You express the green function. It brought to mind multi-channel quantum defect theory.
Yes.
Is there any utility in taking that as a kind of a simple approach to this?
Yeah, it's as far as I know, MQDT is still requires a matrix, so it's n cubed, and we want to stay away from that. But I think the solutions of MQDT could be highly helpful in our case as well.
The interesting separation.
Yes, for sure. I agree. Yeah, it could be useful. You have to ask. There is a theorem that Hilbert proved in 1906, so which I do not fully understand. So the kind of idea is that, I mean, it's not really perturbative because you are putting a lot of this complexity in the calculation. You are putting into inversion procedure here, right? Because you have this determinant which actually does this job for you here in the inversion. So it's not fully I mean, if delta actually goes to 0, it becomes exact. So it's not really perturbation theories, but it's kind of exact solution, but you expand the determinant. Yeah. Well, here you can see that, right? It kind of like, it has this kernel, the trace of the kernel, then trace of square of the kernel, trace of the nth power of the kernel, which is like something like determinant, and then it has the nth power of the kernel. So if it has to be investigated, right? Not many people have tried this method before, so it's still, it's a good question, yeah. Yeah.
If no, we thank Timur again.